Hi friends, here in this video we are going to discuss the concept of inductance of bundled conductor. The concept of bundled conductor was explained in my previous video where I told you that in case of bundled conductor each phase of conductor is splitted into multiple number of conductors. So to understand the concept of inductance of bundled conductor we have to assume a system of bundled conductor. So here this is the system of bundled conductor. So this is forward path and this is return path. Now forward path is carrying current plus I and return path is carrying current minus I. This is minus I. Okay. So return path is carrying current minus I. Now this forward path is splitted into n number of conductor. So it has n number conductors. And this return path is splitted into m dash number of conductors. So these conductors are suppose 1, 2, 3, 4 and this is conductor suppose I and this is conductor suppose n and this is 1 dash, 2 dash, 3 dash, in this way 4 dash, 5 dash and m dash. Here in the system of bundled conductor what we have to do, we have to find the flux linkage of this ith conductor. So what is flux linkage of ith conductor? Because I already told you how to write the expression of flux linkage. So flux linkage of ith conductor will be equals to forward linkage plus backward or return path linkage. So what is forward path linkage? Forward path linkage is we can say it as flux linkage of conductor I due to all the conductors present in forward path. And what is return path flux linkage? It is flux linkage of conductor I due to all the conductors in return path. So we can write the forward flux linkage as mu naught upon 2 pi. Suppose flux linkage due to current in I1, that is equals to mu naught upon 2 by I1 1 upon log d I1. Similarly I2 log 1 upon d I2. In. Similarly, we can write the flux linkage for return path, that is equals to 1 upon 2 pi I1 dash 1 upon d I1 dash. It means flux linkage of conductor I due to current in this 1 dash conductor, that is equals to mu naught upon 2 by I1 dash 1 upon di I1 dash. So in this way we can read these denominations. So I2 1 upon d I2 dash plus dot IM 1 upon d IM dash. Now in short we can write lambda I is equals to mu naught upon 2 pi sigma I is equals to 1 to j is equals to n I equals to n I j, sorry, this is j is equals to 1 to j is equals to n, and then 1 upon dij plus mu naught upon 2 pi to m dash ik 1 upon dik. So in this way we can write this expression. Now we know that this forward path is current I, carrying current I, and this I current is splitted into n number of conductor, and suppose each conductor in forward path is carrying equal current, and same each conductor in return path also carrying same current. So current in each conductor of forward path will be equals to I by N, because there are N number of conductors. And similarly, current in each conductor of return path will be equals to minus I by M dash, because there are M dash number of conductors in the return path. So finally we can write this expression as lambda I is equals to mu naught upon 2 pi, because these all conductors are carrying same current, that is equals to I by N sigma j equals to 1 to j equals to N 1 upon dij plus mu naught upon 2 pi I by M dash minus I by M dash, because the return path is carrying current I and it is divided between M dash conductor, so we can write minus I by M dash is equals to 1 dash to K is equals to M dash. So this is the expression. So now we will simplify this expression. See, on simplification we can directly write lambda I is equals to, see, expand this expression. On expanding we get mu naught I upon 2 pi, expand this, we get, take mu naught upon pi into I common and take this N inside the log, so we get log 1 upon di1 into di2 din. Why we are taking multiplication? See, if we expand this, then we will get log 1 upon dij di1 plus log 1 upon di2 plus log 1 upon di3, and log a plus b is equals to log ab. That's why we are writing this expansion of this expression as this. So log 1 upon plus din, okay, and the power of this is, take this n inside the log, so we will get 1 by n. Similarly we can write this expression as, see, write this expression, this is log, okay. Write this expression, we will get log 1 upon di1 dash into di2 dash dim dash to the power 1 by m dash. So finally we know that log a minus log b is equals to log a upon b, okay. So we can use this formula, so we can write lambda I is equals to mu naught I upon 2 pi log di1 dash di2 dash dim dash to the power 1 by m dash upon di1 di2 din to the power 1 by n. Now we know that inductance of ith conductor will be equals to flux linkage of conductor I upon current in conductor I. So simply current in conductor I is equals to I by n. Current in ith conductor is I by n. That is equals to n lambda I by I, and that is equals to mu naught n upon 2 pi, because this I and I will cancel out. So mu naught n by 2 pi in bracket ln di1 dash di2 dash dim dash by 1 by m dash upon di1 into di2 din 1 by n. Now average inductance of all conductors in forward path is suppose equals to L average. That is average inductance of all conductors in forward path. So what will be? It is equals to sigma, means sum of all the inductance in forward path divided by total number of conductors. Because when inductances are paired, we are dividing it by n. It means if we are dividing the total sum by n, so we can write it this expression as sigma, mu naught, this mu naught upon 2 pi will always be common. Sigma I is equals to 1 to I is equals to n, means sum of inductances from 1 to n conductor. This is in the expression for inductance of one conductor. Now we have to write the expression for sum of inductances of all the conductors in forward path. So that will be equals to log di1 dash, di2 dash, dim dash to the power 1 by m dash upon di1 into di2 din by 1 by n. Now if we take this here, if we divide it by n, then this n will cancel out. So that's why we are not getting n here. We are getting only mu naught upon 2 pi. So this n and this n will cancel out. So this is the final expression for, and this is the expression for average inductance of forward path. Now what is average inductance in another form? So we can write average inductance also in another form, that is equals to mu naught upon 2 pi. Suppose we have to remove this this summation sign by multiplication sign, and we know that log a plus log b is equals to log a plus b. So simply we can write this expression as log, take this sigma inside, so simply we get multiplication I is equals to 1 to I equals to n. I hope you are getting all these concepts. These are all concepts of log. To n. So here di1 dash, di2 dash, dim dash 1 by m dash. So this is the expression. So this is the expression of average inductance. It means we can assume inductance of each conductor in a group is equals to L average. So average inductance means conductance of each conductor in group can be assumed L average. Now there are n number of conductors in the group. So total inductance will be equals to L average by n, because all the conductors are in parallel. So L average by n, so equals to mu naught upon 2 pi, take this n here inside this log. So on taking this n inside the log, we get mu naught upon 2 pi ln I equals to 1 to I is equals to n. We are taking this n inside the log, so we get di1 dash, di2 dash, dim dash, these all are multiplied, dim dash to the power 1 by m dash into n, because this n is taken inside the log, upon, sorry, this log is here, okay, this log is here, upon 1 to I equals to n to the power 1 by this n, and this n is equals to n square, 1 by n square. So if we expand this expression, then we will get the very important relation that inductance of each conductor in forward path is equals to mu naught upon 2 pi log. So on expanding this expression we get di1 dash into di2 dash dot dot dim dash. Similarly, sorry, d1 1 dash. I put I equals to 1, 1 2 dash, d1 m dash. Similarly, put I is equals to 2, d2 1 dash, d2 2 dash, d2 m dash. Similarly, like d I equals to n, so we get dn 1 dash, dn 2 dash, dn m dash, and whole power of this is, suppose the power of this whole is 1 by m dash n. So whole power of this is equals to 1 by m dash n. Similarly, we can write the denominator as d11, d12, d1n, d21, d22, d2n, dn1, dn2, dmn, and power of this whole is 1 by n square.
So friends, finally we get this expression of inductance LF. LF means inductance of forward path, that is equals to mu naught upon 2 pi multiplied by log this. Here you can observe that here for this part distances are taken between conductor 1 of group 1 and all the conductors of group 2, and similarly here distances are taken for second conductor of group 1 and all other conductors of group 2. Similarly, we will take each conductor from group 1 and take its distance with respect to every conductor in group 2. So in this way we get this numerator. And what is power of this numerator? The power of this numerator is 1 by mn, 1 by m dash n. And n is the number of conductors in group 1 and m dash is the number of conductors in group 2. So this numerator of this inductance expression, it is called mutual geometric mean distance and it is represented by dm, and this denominator part is called self geometric mean distance and it is denoted by dsf. So here in case of dsf we will take the here see this part, here we take the distance of conductor 1 with respect to all the conductors in group 1, and here we take the distances of conductor 2 with respect to all the conductors in group 1, and in this way we will take the expression for nth conductor and we will take the distances of all the conductors with respect to nth conductor in group 1. Now here we will take the square of number of conductors whose inductance we are calculating. Here we are calculating the inductance of forward path and there are n number of conductors in forward path. That's why here we will take n square. So these are very important relations and you have to remember this. So there are three very important relations. First is inductance of forward path. See, inductance of forward path. Second is mutual GMD, mutual geometric mean distance. Okay, and the formula of mutual geometric mean distance is this. And third one is self GMD, means self geometric mean distance. So these are very two important formulas and they will be frequently utilized in my upcoming lecture when we will calculate the inductance of various conductor configurations. So you must remember all these three formulas. We know, okay. So now we will meet in my next video. I hope you got all the concepts. Thank you. Jai Shri Ram.